Woohoo! Welcome back. Tonight we're going to be working with partial sums of geometric sequences. Woohoo! And so basically what we're going to do is we're going to take the geometric sequences that we've been working with and we're going to add the terms. And just like with the partial sums of arithmetic sequences, we're going to set it up as the nth partial sum, right there, S sub n, is, remember this is sigma, this is the S, of k, from k equals 1 to k equals n. And then it's the general formula, except this time we're not using n minus 1, we're using k minus 1. So first term is a, then a times r, then ar squared, then ar cubed, all the way up to ar to the n minus 1. Because if we're going all the way to n, the nth term is the n minus 1. So we had a really cool formula from in the last video. There's going to be a similar formula here, and that is that we set up S sub n, but instead of flipping it backwards, which is what we did in 8.2, we're going to multiply by r each term. So a becomes ar becomes ar squared becomes ar cubed, and so on and so forth, until ar to the n minus 1 becomes ar to the n. And then we're going to subtract, or add the opposite if you prefer. In which case, this comes down, we get a, and then it's ar minus ar squared plus the opposite of ar squared, ar cubed plus the opposite of ar cubed. So all of these cancel out, including this one. And all we have left are the a that begins things over there and the ar to the nth over here, which is subtracted. So we get a minus ar to the nth. And then on the left, we factor out an s sub n and we get 1 minus r times s sub n equals, and then I factor out the a on the right. It's a little more complicated because we are dealing with multiplication here. And I get S sub n equals a, up on top, 1 minus r to the n all over 1 minus r. Now, unfortunately, this is not nearly as simple and as necessarily satisfying as the partial sum of arithmetic sequences, but this trick of canceling everything in the middle is pretty cool. So that's why I want to show it to you. So this is the formula that you want to focus on. So let's go ahead and take a look at what this looks like in when we're actually doing something with it. So we want to find the partial sum of this geometric sequence. So I want to go from 1 to 4 to 16 plus, and then keep going to 4096. So first thing I need to do is figure out what the sequence is, and then figure out how many terms I've got, right? I got to figure out all the details. So if my sequence looks like 1, 4, 16, ... 4096, then I know I've got my a is my first term, which is 1. And it seems pretty clear that I'm multiplying by 4 each time. So my r, my common ratio is 4. Okay, so then my general term is going to be a sub n is equal to 1 times 4 to the n minus 1. Now, the cool thing about this is that a is 1, so I don't even have to write it in, although it makes it more clearly a geometric series to write it like this. So the next question is 4096. Which one is this? So 4096 is equal to 1 times 4 to the n minus 1. Okay, so what we got to do is we got to figure out, since that 1 is not going to change anything, really what I want to do is figure out what is the exponent here that makes 4096. So I could use logarithms. I'm not going to use logarithms. I'm just going to use my calculator. I'm going to try 4 to the 5th. 4 to the 5th is 1024. Just got really close. Okay. 4 to the 6th is 4096. So I've got 4 to the 6th equals 4 to the n minus 1. That means that n equals 7. So this is the 7th term. So if I actually wrote out the whole thing, we'd have 1, 4, 16, 64 times 4, 256. 256. And then times 4 would be 1024. And then 4096. So here we've got A1, A2, A3, A4, A5, A6, and A7. So I want this partial sum. So my partial sum is going to be 1 plus 4 plus 16 plus ... plus 4096. Okay, so let us go back to this lovely formula here. So S sub n is equal to A times the quantity 1 minus r to the n all over 1 minus r. So this is going to be 1. S sub 7 is 1 times 1 minus r. My r is 4. 4 to the nth all over 1 minus 4. Does that make sense? Woohoo. So then I've got, let's see, 4 to the 7th. 4 to the 7th is 16,384. So I've got 1 minus 16,384 all over negative 3. So let's see. 1, oops, you can't see it. 1 minus 16,384 is negative 16,383 all over negative 3. I'm going to guess 3 goes into this because I don't think this sum would actually give me a fraction, right? So let me try dividing by negative 3, and I get 5461. So, you know what we can do? There are only 7 terms. So we can check this by actually just adding them all together, which is kind of a pedestrian way to do it, but we can do it. 256 plus 1024 plus 4096, and I get, dun, da, 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 I get the same number. Isn't that exciting? So why is this formula useful? Well, this formula is useful if you have an n that's going to be larger than 7. So adding all of these together would be a pain. Or if these are fractions, if you've got, if these terms are fractional, that's not going to be fun to add them all together. So you can use the formula then as well. Okay, so next question. How would this problem change if the terms were this? So let's take a look. I've got 1, 4, 16, and this is 2, 8, 32. So in fact, this looks like 2 plus 2 times 4 plus 2 times 4 squared. Right? Each one is twice as big, and 8192 is 2 times 4096. So what have I done? I've multiplied every term by 2 instead of each term just has the a equals 1. So there are a couple ways to think about this. I would say that this is equal to 2 times the previous it's equal to 2 times the previous partial sum, And so I could do 2 times 5461, right? The total we got up there. And so that's going to be, clear, 5461 times 2 is 10,922. The other way to do it is to work it out where a equals 2, right? That's what that 2 being in every term, you could just work it out with a equals 2, r equals 4, n equals 7, and then you could work out this where it would be 2 times 1 minus 4 to the 7th all over 1 minus 4, which would give you the 10,922. So there are two ways to look at it. Either we have now adjusted and our a is now 2, or simply you just see it as 2 times each of the terms, so you just multiply 2 times the total. So that's just a quick upgrade if you've got a couple of problems in a row that are related, so it makes it a little bit easier. Okay, woohoo! In the next video, we're going to be working with infinite series. Woohoo! So until then, take care of yourselves. Know that you're amazing and incredible. And woohoo and math on.